Is that the question for the exam? I said, I don't know. Doesn't matter. So long as the method is correct, you can do it. So you can work out the capacitance and get the answer. So I think the next thing is about the energy stored in capacitor, which you know already. There are many ways of calculating. You know already energy stored half CV squared, very well known, or half QV, or half Q squared upon C. So you can also calculate energy. Energy is half D dot E, epsilon E squared integrate over the volume and so on. But this is not true. But this definition, Q upon V, capacitance Q upon V, is valid for any system of conductors, any shape of capacitor, so long as you can calculate voltage between the two plates, positive, negative, Q upon V gives you the answer. Okay. And this, if you know the capacitance, you know the voltage difference between the two plates, whatever be the shape of the capacitor, you can calculate energy stored through these three formulas, no problem. So this is called the energy method of calculating capacitance, which is also possible because capacitance is one definition. Also, you can calculate energy stored. Okay, is integral of the volume E dot D, dV, the volume here, epsilon times E squared, dot product, integral volume dV. This is equal to half CV squared or half U squared upon D. You can calculate the capacitance once you find it. These are other methods. But they leave the same answer anyway, leave the same answer, obviously. So now we move forward to look at an example, simple example, next slide, of the capacitance of a capacitor with two concentric plates, meaning that in the form of a sphere. One of them is the ball inside there, it is 45, and here calculate the capacitance. So for simplicity, of course, assume epsilon naught is constant. There need not be. Epsilon naught could be a function of radius. No problem. Same method. Put a charge of plus Q here, minus Q involved here. At any distance R, calculate the D. And when the D, find the E. Always must find the D first, not E first. D first, find E, get the potential, VAB, integral B to A as usual. E dot dr becomes ER dr, because all the flux are normal to R. Again, you can calculate that the capacitance given by 4 pi epsilon, 1 over A, 1 over B, and you can see that you can get the result we discovered just now. If the second conductor is at infinity, B times infinity is goes to 0, which is the result we discovered earlier, which is 4 pi epsilon divided by 1 over A becomes 4 pi epsilon A, which we have found out already just now. But the methodology, the method is the same. And you have to go to Gauss's law for D, not E, D. If you use E, strictly speaking, you are incorrect because you have to take into account the charges even in the dielectric. You can also do the same problem but after the energy method, same method, and get the answer. Okay. Now we look at another problem which is part of the tutorial. It's already done also there, which is a cylindrical, a coaxial cylindrical capacitor. Again, the same method, same methodology. Calculate D, Gauss's law. Charges on the metal conductor, inner conductor, outer conductor. Charges inside the dielectric Do not count, ignore completely, because you are going to use also rule for D. This is something that's not well realized, but if you use E, you have to take into account pluralist charges. You get the final answer, yes, but strictly speaking, is wrong. When a dielectric is not air, the dielectric can be polarized, meaning that they can distort atomic structure, molecular structure to have plus minus inside the dielectric. So, let's go back now. Assume the capacitor is of length L, the medium constant epsilon r, inner radius A, outer radius B. Okay. Because of the charges in the conductor, I put as Q, lambda L per unit length, lambda coulomb per meter per meter. So because of the source of the charge, the cylinder, therefore the Gaussian surface GS is cylinder also. Cylinder of radius R. The cylinder of radius R, because of the symmetry, all the electric field or the D will be normal to R. So therefore there is symmetry. Therefore integral D dot ds over my Gaussian surface must be closed. My Gaussian surface, which I'm taking now, is here. Cylinder, closed cylinder. So closed cylinder, so you can see now we see the outward flux integral to ds. Surface on the left, dr is parallel to the surface here, therefore no mode is 0. First contribution 0 here. Right hand side is also 0, parallel to it. What is left is the flux coming out of the curved surface of the cylinder. So, is constant here, we're given R. So dr multiplied by the area of the curved surface cylinder, the area is the cut, 2 pi r multiplied by L. So you get a rectangle of length 2 pi r of height L. So the area is 2 pi r times L multiplied by dr, is the answer. So 2 pi r times L gives meter square. dr is coulomb per meter square. Meter square cancel, coulombs on the left. On the right, charge enclosed, coulomb, then flip the charges only on the conductor and pull the Gaussian surface, which is the plus Q, not plus on the L. Of course, there are charges outside the Gaussian surface, but you do not take into account, and you see already they do not count. Only the charges enclosed by the Gaussian surface. You know what Gauss's law says? Enclosed. Enclosed means found inside. Enclosed. Inside, not outside. So therefore, from here I can find dr, epsilon dot dr, I can find er. And here, if epsilon is a function of r, you can see here is a function of r. Epsilon here, I can find dr function of r, I put it there, no problem, I do it, final answer in equivalence. So the capacitance of this capacitor of length of width L is given by 2 pi epsilon and L, or epsilon epsilon naught and R times L over log, natural log of B upon A. So when you are involved with cylinder geometry, you always have a log of ln. When dealing with spherical, you have the potential to go 1 over r, because you have integrated E dot dr, 1 over r dr, natural logarithm of log r a to b, log a minus log b, minus plus, log b minus log b upon a. This is maths. So therefore, I have the capacitance of the length L. I can define the capacitance per unit length, because for a long cylindrical capacitor, it doesn't matter where I take the section, I I can have defined capacitor per unit length, which I indicate by a small head on top, 2 pi epsilon, ln of B. So I can now, if I look at the long cable made of small section, these capacitors are all in parallel because they are the same potential terminal. The inner conductor is the same, outer conductor is the same, they are the same voltage, therefore they are in parallel. Therefore, you can see if I have one here, another one here, they add together many of them.
Sir, do you mind lean to the right? Because I'm recording the video.
Oh.
Yeah.
Okay?
Oh,
Now,
lean to the left.
Actually, just don't lean all the way to the right, it's okay.
no, what are you asking?
Okay, assuming a transmission line, then I can roughly use this formula to calculate the capacitance of the
So this is where the origin, you have to know the capacitance of this capacitor, transmission line. And if you know the inductance per unit length, you divide one by the other, you get, take the square root, you get the characteristic impedance. This one, so you have a long cable, again the same dimension. I can carry the capacitor, 2 pi epsilon naught epsilon r, as you found out here, per unit length, or ln u. Okay. So one can find the inductance, for the case of the conductors again, because you have a current, you find out the LC is mu epsilon relationship. Therefore I can calculate what is L. Okay? So I can calculate what is L, and then I can find Z naught is square root L and C. Is called the characteristic impedance, which Professor Go will tell you when time will. So I say 50 ohm line, it means that you calculate the line, the cable, capacitance, calculate inductance per unit length, and you divide the square root, you get 50 ohms. Okay?
what's the cable, right?
Yes. But this formula is valid for all conditions, whether coaxial, whether whatever it is, twin wire line, whatever it is, so long as you know C, you know L, take square root, you get the doesn't matter. So, this is what here. So what is L? L is given by, this is a relationship that's very useful. That's given by mu epsilon upon C. C is 2 pi epsilon ln B upon T. Okay, so cancel. Epsilon cancel, of course, because inductance cannot be function epsilon. Is mu upon 2 pi ln B. Now if you take this and you divide this, what do you get? So Z naught square root L upon C give you L square root. L is given by mu ln B upon A divided by 2 pi divided by C. C is on top, ln on top, ln B upon A, okay, divided by 2 pi epsilon, that's it. Okay, so you work it out, you can see, divided right there on top. Okay. So the answer will be 1 upon 2 pi mu upon epsilon ln you encounter this later. You will read this later when you talk about observable property. So, if you know the what is this property? This is a air dielectric. For dielectric, mu is same as mu r and mu naught. Dielectric 1. Epsilon is epsilon naught, epsilon r. Substitute, get the answer. You get the answer. So many ohms. 50 ohm line.
So this will be the one
But the cable is fixed already, what? You cannot design the cable. Cable is given to you. This value is given to you in the specification of the cable. Are you going to make a cable? Can't make a cable. This is given to you. 50 ohm line, or in the old days the TV line, 300 ohms, twin wire line. All that. But this is just to show you the origin of this type of unit. But what is important to note is that if you have a coaxial cable, the characteristic impedance is a function of the dielectric phenomena, assuming mu is 1, and magnetic, the function of the inner radius and the outer radius. Okay? And it doesn't depend on the length. Whatever with the cable length, the property of the line is the same. A 50 ohm line, whether it's 5 cm or 1 meter or 30 meters long, the property is the same. Right? Same. So normally the cable, you don't design the cable. You are given, you do the design to get the cable that you want. And then you pick it up from the specs, from the store, whatever it is, and you get it. It's not easy to make a cable. Okay, so let's go on further now. So now this is just to review what you have learned before. Capacitors in series. This is A, this is terminal AB, they are in series. You can see this plus Q minus Q minus Q induced plus Q minus Q and so on. So the voltage across them V1, V2, V3 add up. This is how we get the formula. The formula, the voltage across each capacitor V1, V2, V3 add up. So V1 is Q upon C1, the same charge. V2 is Q upon C2, V3 is Q upon C3. Therefore, 1 upon C equivalent, the total voltage, okay, is the same as V1 by V2, V3. You simplify. V1 is V2 by Q is 1 upon C1 1 upon C2. So you notice that this formula for parallel capacitor, for series capacitor, is the equivalent of the formula for parallel resistor. Now let's look at capacitors in parallel, which you know already. So in parallel, the same voltage V. So Q total charge, Q1, Q2, Q3 add up. Finally, we know already capacitors in parallel add up. Q1, C1 plus Q2. As I said, formula is opposite to those of resistors. Now you remember. Okay, let's now look at the example of how do we apply this formula. Not necessarily exam, Mr. Spotter somewhere. Not necessarily Mr. Spotter somewhere. After you either exam, just spotting as you go. This is for learning, not spotting. You were spotting, so what? If you know the concept, you can do any portion. But if you memorize, you're dead. So we're going to apply this concept right here like that now. I have a capacitor, a cross-section, this way. Radius A, conductor. Okay. Radius B, no conductor, it's on R1. This on R2. This is C. This is the conductor. Using the result of just derived, what is the C total of this capacitor per unit length? So this is the conductor. You have free charges. This is the conductor, free charges. The two dielectric, I've got no free charges in between. No. There are many ways of solving that problem. The simplest way would be to use the formula we derived, trying to find out which one is in parallel, which one is in series. What is this? You have two capacitors here. So you agree with me that the electric field will be normal. Okay? So we can do the problem from first principle, but there is no need, because this consists of two capacitors. The inner capacitor here, because this can be looked upon as if it's a pseudo-conductor, meaning it looks as if it were a conductor, because the potential here is the same. Therefore, this interface between the two dielectric, because dielectric is symmetrical, is an equipotential. Right? Because everywhere the field is normal to it, an equipotential. But of course, it is not a conductor. It need not be a conductor, it is an equipotential. So therefore, this is equivalent to, say, C1. I call it C1, right? This is equivalent to C2. So we have two capacitors here. Capacitors C1 is made up of dimension A and B. A and B. Capacitor C2 is made up of dimension B and C. Right? So you fill in the blanks. Now those two capacitors, are they in series or in parallel? You can see that if you go at this point the same, so it as if you have this one under the capacitor here like that, this one under the capacitor here. They are in series. It's C2, it's C1. So total capacitor, they are in series. Why? Also because the voltage from across these two and these two can simply add up. So therefore I can write down C1, use the result, 2 pi epsilon naught epsilon R1 ln D upon A. C2 is 2 pi epsilon naught epsilon R2 over ln C upon B. Okay? So therefore, they're in series. C1 and C2 are in series. So therefore, you make your own total. Capacitor in series, the inverse of resistors, R, the formula. So say that two of them, 1 upon C1 plus 1 upon C2 become C1, C2 over C1 plus C2, right? You understand? Yes, the simplest method is using circuit theory. That's the reason why people use circuit theory. Once you have derived some result from fields, you can make use of it directly. Okay, let's extend this to another example. Nothing to do exam, just to enlarge our knowledge. The bread is in conductor, as usual. This is A. This is A. This is C. Now my capacitor is missing. So here, this one R1, this one here, this one R2. Calculate the combined capacitor. You do yourself. half of it is the capacitor. C1 is half of it, another capacitor C2, we have to calculate the half of it. Are they in parallel or in series? In parallel, we can see it because you can see at this point here, the same potential, so therefore these two in parallel. We can calculate C equivalent. C total. But of course, when you calculate the formula, don't forget that the capacitor, when the whole capacitor is 2 pi epsilon ln something, for half of it, of course you take half. Because 2 half with 1 whole capacitor in parallel, so you take half of it. So half of the first formula, half of 2 pi epsilon naught epsilon 1 ln not B, C upon A. Sorry, can I change this? Because I put C there. Put B, so you're more used to B. B upon A. Next one is half of 2 pi epsilon naught epsilon R2 or ln again B upon A. In parallel, it's 100 together. Okay? 5 minutes. So let's make a bit more complicated. Same geometry, same picture. So now I have this. This is on 3. It's on 4. You name it, you have it. Okay. So now you can go and work out the way you want to work out. This dimension is give it as you can see no. Never mind. I got this one D for the sake of not confusing you. A is one A is one B for this G. So the radius inside there is G. Okay. So the one on the left, so one is radius is inner radius A, outer radius B. Now I've added another part of it. Epsilon R3 radius, the radius is G. Okay, inner radius means that A, and then epsilon R4 same. So you can calculate now. What is the capacitor? Capacitor, this combined capacitor. Of course, you have to look carefully and see which one are parallel, which are in series, and then do it. So therefore, you must know how to check whether something is parallel or in series. You cannot spot. You spot. Answer changes the result. The question changes the date. So, you can think it for yourself. It's a new problem. moments. Okay, so let's now look at the oil problem. The first one is based on what we discovered, what we did last time. The electric field coming from the loop, which I'm not going to discuss, we already done for you in the oil here. Electric field to the loop. This first problem is done already in the lecture, explained across already, and the solution is here. I will discuss question number 2. Okay. So please go to the solution, look at the various explanation there, and see whether you understand or not, because all of these have already been explained in class already. So we are going to look at question number 2. Question number 2 is based on Gauss's law. Tutorial 2, question number 2. Tutorial 1, question number 2. I take it you have the tutorial in front of you. Tutorial 1, question 2. Question 1, we discussed already in the lecture. Everything talk about it will be given there. So question 2, you have two large interconnecting. Question 2, carefully. Infinite plate. This is A, this is B. Parallel each other, although each other density of plus sigma. So you have to find the field, of course infinity long. Find the field on this side, in between 3 regions. Find the field in between the plate, on the left, on the right. And the solution given to you there. Now to do such a problem, if I put it vertical, I have to define a positive direction, and then define going to the right as positive, just for the sake of I take that positive direction. That's X. So I'm going to find electric field in the 3 region. To follow the solution, and we call the same point P. So in between the sheet, on the left of the sheet there, on the left of the sheet, here. But before I do this, I have to use a result, derive a result. I have an infinite plate of charge. Already, this is plus sigma. By symmetry, I expect the field to be 90 degrees and uniform. I'm going to derive the result for an infinite sheet of charge of positive sigma, Coulomb per meter square, and use the result and use superposition. Superposition means at the given point P, I shall find a contribution at P due to A, the field, then find a contribution at P due to B, add a subtract dependent direction, and that will give field at the point P. So the first method I will explain now, I'm going to follow my solution, and I will show you another method which is less likely to cause you make a mistake. But let me follow the solution first, my solution. So we found out already that this is an infinite plate, rectangular. I will draw a small Gaussian surface here. Okay. So here I have field D, D1, this is D2. By symmetry, D1 will be equal to D2, symmetry. Okay. So this is small element, this is small surface area, delta S. Okay, so therefore now I can write down now Gauss's law. Integral dds, left hand side, D2, coming out, delta S positive. Right hand side, plus D1 delta S positive, coming out, flux theorem, not field, flux. This come out left, right, does not come out left. No, it's not the field, it's the flux that I want coming out of the surface. The contribution to the left is 0 because parallel to the surface is 0. This is equal to sigma S, sigma times delta S. Okay? Now, so therefore delta S cancel. Therefore D1, we saw D1 or D2, D1, D2 is equal to sigma S, sigma, what is sigma S? Sigma S, I don't know. Sigma S. Okay? D1 by 2, because those are equal. So D1 plus D2 is equal to sigma S, therefore D1 equal to 2 is equal to D. Therefore D, the result of our U is that D is sigma S upon 2. So the electric field E, which is D, assuming is in air, I think it's given in air, I don't remember. Given in air. I think it is in air. So therefore, this is a result we shall use that the electric field normal coefficient of charge of density sigma S coulomb per meter square is given by sigma, not sigma S, sigma upon 2 sigma. So now let's move now. This is positive X. You have to be very extra careful now what we do. This is positive charges here. Therefore, electric field will come out this way. Okay? So the contribution due to this one now, E at P, due to A, here, this doesn't contribute, and this one is minus AX. Forget about AX, but AX is sigma upon 2 positive. So it's going this way. This doesn't do anything because it doesn't pass there. So now, by superposition, I'm going to superimpose the answer, the contribution coming out from the negative. By negative, one negative charge, remember, that is. Being negative, the field goes inside there. So therefore, EP due to B is given by, at this point, this goes to the right, it passes to here. This has got nothing to do with it, it's on this side. It is plus sigma upon 2. Combine together, 0. EP at A, 0. Cancel out, right? Because this is by positive. Superposition. So similarly, you can see if I find the EP due to A, I call EP, not like EP at home, let's call it this point here. P2 to save the P2. EB at P2 due to A. Again, due to A, this is coming, this one here, goes to P2 here. Therefore, the answer is sigma go to the right, sigma go to epsilon naught. EP at P2 due to B come this way, at this point, minus sigma upon 2 epsilon naught, answer 0 again. EP2 to 0. Okay? Notice carefully that because I have drawn the arrows going into the negative charges, I have already counted the fact that they are negative charges. I cannot put negative here. Double counting. I cannot. If I'm going, if I owe you $5, I cannot say I owe you minus $5. If I owe you minus $5, then you owe me. Cannot double negative. Then now let's look at the center now. Okay, everybody? Okay, at this point here, P3, I call it P3. So E at P3 due to A, the first thing here, going to the right, sigma 0.20 naught. E at P3 due to B, going to the right, add together, we give you EP3 due to both is equal to 2 times, which is 2 times sigma 0.2 epsilon naught, which is sigma 0.2 epsilon naught. Okay. Down here going to the right. If you want to put vectors, you can put it if you want to AX. Okay. So this is the fault, that's the mistake people usually make, because we use the formula sigma 1 epsilon naught. They think that if sigma is negative, they will have to put negative sign. Of course you can put negative sign provided you do not double count. So we show you a method that doesn't have to give you so much stress, much faster, no problem. So you assume, even if negative, assume all positive. And then later you finish, and then you add the negative where it is necessary. Okay? This is A, this is B, same. So I shall assume they're all positive. I said just positive. I shall assume it's positive. So I call it sigma 1, sigma A positive, sigma B positive. Assume all positive. Again, this is positive X. At this point here, P. Again, if I draw my curve now, positive, positive, like this, like this, like this, like this, no problem, because all taken as positive. So I calculate E at P due to A is given by this one here, minus sigma A 1.2 epsilon naught, EP at B due to B at this point here, this one goes to the left, minus sigma B 1.2 epsilon. Is that okay, everybody? I haven't done anything, I just call a new variable sigma sigma. Now I join them together, add them together. Sigma A is plus sigma, sigma B is minus sigma, if you remember. It's the same thing. You cancel. So the final answer resulted EP at A equal to 0 minus sigma 0.2 epsilon naught plus minus minus plus 0. We did not double count. We just say, okay, instead of taking the charges to be negative, let's take an all positive, call a new variable, sigma A and sigma B. Pretend as if there are the charges coming out, positive, positive, coming out, coming out, coming out, coming out. Later, put the appropriate sign if you compare those two. The same. Of course, here I have added this way without taking minus. Right here, I assume it is positive. Later on, I replace it by minus. The pick is yours, the choice is yours. You take what you want. This method particularly useful when you have many sheets of charges where you don't get mixed up. So you assume all the charges are positive, or the electric field coming out away from the field of charges. You work it out vectorially. Later on, you replace by the appropriate sign given to you. That's the answer. The same thing. This avoids you from making mistake of double counting. Some people, without thinking, memorization, spotting question, negative here, and then when he calculated this, he forgot that this is going this way, he put a negative here. P2 here. Put negative, but then he has the other way. You got a field which is non-zero here, nonsense. Okay? So up to you. The selection, the pick is yours, the choice is yours. So you do the same thing for the in-between, you find the answer will be sigma 2 epsilon naught. So you assume all the charges are known, sigma 1, sigma 2, sigma 3, sigma 4, whatever, positive, all the electric field coming out from the charges, then you find the resultant vector, and later on, plug in the answer given to you if the charge is sigma b negative, this will be minus sigma. And this method can be used by any number of sheets, charges, provided you do not double count, you do not double count. Okay? So next week we shall talk about Gauss's law. If you give me some time to sit on it a bit. The solution given to you also, how I choose the Gaussian surface. The solutions are exceptionally detailed, very, very detailed. And in my own handwriting, in my own way of doing it. Let's do an example. Mr. Spotter is going to say it's exam. Mr. Spotter is going to say exam question. Of course, it did not be like this, it would be this way. I'm just drawing this way, easier for me to save paper. So, sigma minus 2 sigma plus 3 sigma minus 4 sigma sigma minus sigma. I just want to make the charger balance out just for the sake of recursion. So you can see you have a mixture of plus and minus cut in the field all the region, for example here. PM there. So it's again the same thing, is superposition, but again to make life easier, call it sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, positive direction here. Okay. And then now I can write down my answer. So of course positive, coming out, 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 coming out. So we don't care because this one you don't care what that means. Positive. So we can write down PM, E at PM. For this one, positive, sigma 1 upon 2 sigma naught. For this one, positive, sigma 2 upon 2 sigma naught. For this one, negative. This one, negative. This one, negative. And now you put the appropriate value. This is 4 sigma minus 2 sigma plus 3 sigma minus 4 sigma. This one is minus sigma. That's it. Cannot go wrong. Because you have assumed all positive, so you have no danger or risk of double counting if you use the first method, which is the solution, which I told you. Or that you try the two methods. Of course, two methods give the same answer, but you have to make sure. One method here, you can go up with the risk of double counting. Because if you say the field, the active field is going to negative sigma, and then later you see the field that goes here is minus sigma over epsilon naught, means your field going this way. Nonsense. Okay, so we shall stop here.
Perfect.